I was looking at what we're covering today, and then I started to have mixed emotions. Here's why. If I had to say, of the material in chapter 4, what is going to be most useful going forward, it will be the things we're talking about today, which I always feel like is bad form to talk about stuff that's pretty important on the last day before a break. But then I started having other mixed emotions of, well, but it's not really the last day before a break. You know, so other schools I've taught at, I'd be concerned that 95% of their class was going to get plastered right after class. I'm less concerned about that here. And so I feel like you might retain something.
Especially right thing is happening.
Particularly with this lovely spring weather we're having. Anyway, so I guess moral of the story is, hang on to your hats. I'm going to be trying to get through a fair chunk of material today. And of course, if I fail, we'll just pick it back up after spring break. But I'm also going to be talking about, like, don't take the fact that I'm going to be doing computations. Don't let that fool you. The things I'm going to be talking about will be kind of essential going forward. So, first of all, last time we talked about the word orthonormal and what a set of orthonormal vectors are. And someone, I've given you guys a disclaimer about my spelling, right? Yeah. I feel like it's usually in my monologue in the first day of class. My spelling is atrocious on the board. My arithmetic's atrocious on the board. It makes sense that spelling that I'm not very good at would also be atrocious.
So it's like a mathematician.
Right, but someone, I guess, was failing the procedure that I like to lay out in my class. Tyler was commenting that someone was making fun of my spelling, which that is perfectly acceptable. I just asked that you do it to my face. And then you help me spell the word correctly. So I guess I had an A where an O went in the orthogonal.
I wouldn't have noticed.
Cool. So if you didn't notice, that's fine, but so orthonormal vectors is a set of vectors with what? Two properties. The first property is Qi dotted with Qj is 0. So that's not a very good J. That was a 2. As long as I is not equal to j. And the second property is Qi dotted with Qi is 1. Right? That's what it means for the set to be orthonormal. So really, what are we saying about here? They're all unit vectors, they're all unit length 1, and they're all pairwise orthogonal to each other. Of course, you can't be orthogonal to yourself. Oh, well, maybe you can. That'd be cool. Name a vector that's orthogonal to itself.
Zero vector.
Zero vector. Yeah, but these are non-zero vectors because they are unit vectors, right? So, okay, so if we've got orthonormal vectors. So, first thing I'd like to prove to you today, every set of orthonormal vectors is independent. I'd like to prove that to you today. So this is, we'll call it a theorem. Theorem. V or N. Theorem. This is going to be a proof. Okay? So I hand you a set of orthonormal vectors. I want you to be convinced that just by the act of making them orthonormal that they are independent. Okay? So what are we given? We're given like Qi to Qn, okay, are orthonormal. Or we need to show that some linear combination will say alpha 1 q1 plus dot 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 plus call it alpha n qn equals 0 implies that alpha 1 equals dot 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 equals alpha n equals 0. Right? That's what we need to show. Agreed? True, false? True. How do we show a set of vectors is linearly independent? We show that the only linear combination that is a 0 vector is the combination where all the coefficients are 0. Right? Okay, so let's take our linear combination. So consider alpha 1 q1 alpha n qn equals 0 and multiply by Cedric, what's your favorite natural number? What? What's your favorite natural number? Counting number. The numbers you learned in like first grade. Like seven's great. Seven's great. So we're going to multiply by q sub 7 for Cedric. Transpose. Both sides of the equation. Fair enough? So I'm multiplying the left side of the equation, but now I have to, I need my, I think something's going to be important here. I should probably pay attention to what happens on Q7, right? And of course, if I do something on one side of the equation, I ought to do it to the other, right? So on the right-hand side, strike that. On the right side of the equation, what is Q7 transpose times the 0 vector? It's just 0, right? On the left side of the equation, what happens? Let's look. We get alpha 1 Q1 transpose Q7 transpose Q1, right? But then we get alpha 7 Q7 transpose Q7, and then we get alpha n Q7 transpose Qn, right? Just distributing that through. What do I know about these vectors? What kind of vectors are they? It's an orthonormal set of vectors, right? In other words, what is Q7 dotted with Q1?
0.
So what I get here is alpha 1 times 0 plus, what do I get here? Q7 dotted with Q7?
1.
So I get alpha 7 there, right? And then what do I get here?
You get 0.
Alpha n times 0. So in other words, what do I get when I do Q7 dotted with Q2?
0.
So do I get a 0 everywhere except for here where I got a 1?
Yes.
So the left side of this equation is just alpha 7 equals 0. Is that fair? We're okay with that? Okay. Now, was there anything special about Cedric's choice of 7? I don't think so. Could we have done this for all the natural numbers from 1 to n? And would the conclusion at the end of doing that for each of those been the same, that alpha sub the number that we just did would have to be 0? So what did we show? We took a fixed linear combination. Alpha is a fixed number. It's not variable. It's a constant. It's like the golden ratio or E or pi. It's a number, right? It's just we don't know which one, so we put something generic there to placehold for us. So we've got all these fixed alphas that gives me the 0 vector, right? Got a fixed linear combination. I've chosen one. There it is. And what did I show you about all of the coefficients in that? That they all have to be 0. In fact, I think what we showed here is that there's only one linear combination of those vectors that gives us the zero vector. And it's when every single coefficient is zero. Am I done? Did I prove that they're linearly independent?
I'm not sure.
Yeah, let's do democratic math. Yes, the proof is complete. The vectors are linearly independent. No, you've left me totally unconvinced. The vectors could be anything. Let's vote.
You did that really fast. I couldn't really follow it.
Oh. So, I guess what you're saying is you don't know because I went too quickly through the calculation?
Yeah. You don't have time to write it, watch, and listen, pay attention.
Yeah. I was never successful at writing math fast enough in a class to be able to also process and think about what I was being exposed to. It's part of why I do those agendas for you, so that you don't feel compelled to write everything, but. So what was the idea? I chose some q sub, say I multiplied both sides of the equations by that q sub I, and then I looked at what happens on the left side. Unless the I is equal to the subscript, I get 0. Q sub 7 dotted with Q1 gives me 0. The only way I don't get 0, like Q sub 7 dotted with Q sub 2, which is in here somewhere in those dots, gives me 0. It's only when I get to Q sub 7 dotted with Q sub 7 that I get something that's not 0 and it's 1. So that's what I wrote here. There's the 1 and there's the zeros. But then I look, okay, so alpha 1 times 0 is just 0. I can forget about it, right? If I was Italian, maybe I could say that. So the only thing I'm left with on the left side is alpha sub 7. On the right side, it's pretty clear we're multiplying something by the 0 vector, so we just get 0. So the act of multiplying both sides by q sub 7, on the one hand, left me with just one particular coefficient, alpha sub 7, and on the other side, left me with just the number 0. But we said that's pretty generic, right? There's nothing special about the number 7 there. I could have done that for alpha 1, alpha 2, alpha 3, up to alpha n. And so I get all of the alphas, all have to be 0, therefore, this linear combination of these vectors that equal 0, the only way that can happen is if all those coefficients are exactly what I showed they had to be, which are 0, therefore the set is linearly independent. So we are done. Usually at the end of a math proof, you can like do a little box.
Q.
Historically, you would do like QED, which is Latin for that which was to be shown or something like that. Well, it's an abbreviation for Latin. Okay, so that's a fact that you should have tucked away in the back of your head somewhere, that a set of orthonormal vectors are linearly independent. Okay. I thought I saw a hand. Was there a question?
Yes.
Okay. So it was like a pump fake. Okay, so we talked just briefly about orthogonal matrices, and we said the kind of defining characteristic of an orthogonal matrix was this, right? Q transpose Q equals I. Remember, sticking with the same convention, capital letters in this class pretty much are always matrices. So capital Q is a matrix where the columns are. So here's something that's a little weird, right? Can you tell me what the inverse of Q is?
Q transpose.
Sure looks that way, doesn't it?
Sure does.
Gold star, isn't that?
Okay, so, yeah. You both can have gold stars at your level. So Jeremiah, you're right. Can a matrix have an inverse if it's not square?
Oh, no.
Yeah, so
I have
if
gold
you
He gets blue one.
yeah, pass him. Yeah, you can lose it. Of course, we haven't done the poker chip ranking system on the colors of the stars yet, so we don't know whether the blue or the gold are worth more. We're too distracted. So, if Q is square, it makes sense to talk about what the inverse of Q is, and I think this pretty clearly demonstrates that the inverse of Q is Q. Okay. So,
So if we have a rectangular shaped cube, it's still gonna leave this
I'm going to blow your mind with rectangular shaped Qs here in a minute.
because everything else will go to, all the stuff that isn't square will go to 0.
Yeah, so you just hang tight. We're gonna mess with your head here.
So if Q square, it forms a basis
Of what?
of dimension R of the length of the size.
I mean, so what subspace are you talking about? A basis of what subspace?
Of R of n, where n is the size of your vector.
So, I mean, the columns of Q form a basis for Rn just to begin with.
Yeah.
In fact, what many people might call, the standard basis, right? Because they're all like, in R3, they would be the vectors that you know and love called I, J, and K. Might be an example of unit vectors that are all orthogonal. It's not the only set of orthogonal unit vectors in R3. Yeah, there's an infinite number of such things. Maybe, so let's run with this, right? Talking about a basis, let's look at a basis of R2, right? So R2 has, one basis would be the set of vectors 1, 0, 0, 1, right? You agree with that? That's a basis for R2? Isn't it an orthonormal basis? I feel pretty good about that. Can you come up with a different orthonormal basis for R2? How about, just for fun, let's do let's go this. Are those orthogonal? Do their dot product. What do you get? 0. So they are orthogonal. So cool. Are they both unit vectors? Okay. Can you come up with another orthonormal basis for R2, different than the two I've demonstrated? Okay. Can you come up with infinitely many? No, because R, real, R. Yeah. And then, something like, I don't know. Well, we could do this a variety of ways. One just might be cosine of theta plus 90. Not 9 theta, 90. In fact, that, by the way, is what I did in my head to get this. The theta I chose was 45. Fair enough? Am I forcing those to be orthogonal? I think I am. Am I forcing them to be unit length? I think I am. Okay, so in our head, I feel like we often think of a unit vector a little bit too specifically, right? A lot of us like to think of unit vectors as like a 1, 0, 0, 0, 0, 0 type vector. They don't have to be that way, right? And we know that. We know that you take any vector. How do you, if I give you a vector v and it's not of unit length, how do you give me a parallel vector of unit length? We're going to use this in a minute, so this is good to bring up now. So, suppose v equals 1, 1, 1. Give me a unit vector in the direction of v. Yeah, so unit vector in direction of v is, well, here's one of them. Right. Notice I said one of them. What's the other? You could do that, right? Usually, well, depends on what we mean by parallel direction, right? How do you define two vectors being parallel?
They have no solution.
No, I mean, I think u and v and u are parallel. There's two R's there. They're, no, one R. There's two letters somewhere. Parallel. Use the symbol.
That's why we have symbols.
That's why we have symbols. If and only if v equals alpha u for some alpha. Could be negative. Right? That's the usual way to define parallel. So, depends on what you mean by direction. Okay. Enough of that. That's kind of a digression. It's time to go to Graham-Schmidt. So I'd like to prove, we'll do this some other time. Orthogonal matrix. Here's a fun fact. This property tells you that when you take an orthogonal matrix, you multiply some vector by that orthogonal matrix, you get a new vector, right? The thing inside those symbols mean the length of the vector, right? So this makes sense. This is really a vector in here. Well, here's a fun fact. Any orthogonal matrix has this property. You don't change the length of the vector. Okay? We'll prove that at some point. That property of Q makes Q something we call an isometry. Iso meaning same, metry meaning like measurement length. So isometry means same length. That's something in mathematics that I like that they want.
Is that similar to how we did the polynomial space in real?
Can you be more specific?
Where we said that for every member in real space, there was a member in polynomial space plus one, or something like that.
Oh, when we were doing like the, when we were coordinatizing vectors from a polynomial space to write them in like Rn? No, because this is just simply talking about a vector that could be an Rn. We multiply by this matrix Q, and this means we didn't change its length when we multiplied by Q. We certainly could change the direction, probably do, because if we don't, that means Qx equals x for all vectors x, which is why would we multiply by Q, then Q is the identity, okay? What does this say though? It says, whatever length that vector had to start with, we probably moved it, but it didn't change the length.
So back to line vectors. Can you move anywhere you want?
Can vectors be moved anywhere you want? I don't know. Okay, so we're about to do the part that Tyler's been looking forward to. He's been very excited to watch me perform Graham-Schmidt on the board without screwing it up. I've got two possible candidates. So, what's the goal here? I haven't told you what the Gram-Schmidt process is, and I'm just going to demonstrate it for you. This is an algorithm. It's something that if you're a computer scientist, you might want to go try to program into a computer and see if you can do it, just for fun, because that's what computer scientists do with algorithms, right? So, what's the goal? I'm going to start with some vectors. Let's call them V1. And what am I giving you here? So I didn't leave myself space. V2 and V3. Didn't leave myself space, I'm sorry. So I start with three vectors. Okay? Is that set of vectors, are those three vectors orthonormal?
Depends, is that a
Okay,
zero or a six?
first of all, I think we can argue that they're not normal vectors. Like they're not unit length, right? V2, for example, is pretty clear that has length 2, which is different from length 1. So, not orthonormal. My guess is they're probably not orthogonal either. For example, V1 dot V2 is 2 root 2. If they were orthogonal, it would be 0. Okay? So I have the steps for Gram-Schmidt laid out on the agenda. What's going to happen here? The goal is we use the Gram-Schmidt process. And it gives a set of vectors that span the same space as the original set. In this case, it'll be as same space as V1, V2, and V3. But are orthonormal. So, in other words, I hand you a set of vectors that are not orthonormal. You run Gram-Schmidt. You get a set of vectors that are orthonormal and span the exact same space. It is brilliant. So, for example, we could look at, well, I've got the three vectors there, but conceptually what's going on here. Any two vectors that are not parallel in R2 span all of R2, right? But could those two vectors be almost parallel? Could they look like this?
Yeah.
And they would still span all of R2 though, right? Okay. Well, the idea is I hand you those two vectors, you hand me back two vectors that span the same space but are orthonormal. And it's even a little better than that, right? If I somehow force an ordering on these vectors, like first vector, then second vector, Gram-Schmidt process hands you back an ordered set of vectors, and the first vector will span the exact same space as the first vector you handed me. In other words, the first vector of Gram-Schmidt is parallel to the first vector you handed me. Does that make sense? So you hand me two vectors. Well, the first vector I give you back from Gram-Schmidt is parallel to the first vector. And then I look at, okay, well, what about the second vector? Is the second vector of Gram-Schmidt parallel to the second vector you handed me? The answer is absolutely not. But the space spanned by the first two vectors you handed me is the same as the space spanned by the first two vectors I hand you. So if you hand me 10 vectors, you could say, well, I want an orthonormal basis for the space spanned by the first 7 of my 10 vectors. What do? You take the first 7 of the vectors that you got out of Gram-Schmidt. Does that seem reasonable? So, how do we do this? Tyler's been looking forward to this. Well, the goal, right? Remember, when you hand me like a single vector, I have to hand you back a vector that spans the same space. So in other words, they have to be parallel, right? So the vectors we get out of Graham-Schmidt, they're going to be an orthonormal set. So what are we going to use to represent them? Lowercase q's, right? So the first vector, q1, it's pretty easy to get. It's got to be parallel to v, but unit length. We know how to do that, right? Just v1 divided by the magnitude of v1. Does that seem fair? Q1 is easy. Q1's not too bad. Q3 and above, buy a computer. I mean, that's not true. I'm going to be doing Q3 on the board for you here, right? But okay, so let's, for our particular vector here, what does that actually give me? Well, the magnitude of v1 is 2 plus 2 plus 0 square rooted, right? And then, of course, v1 was root 2, 0. So I think q1 at the end of the day is 1/2 times root 2, 0. So that's q1. Okay? And we definitely need q1. It is our friend. We will be using it to find q2, in fact. So in order to find q2, I'm going to take u2 and divide u2 by the magnitude of u2. Now, you might ask, Brent, I don't see a u anywhere on the board. That's right. We have to figure out what u is. Okay? It turns out, yeah. We gotta figure out what u is. Right? What u is. Yeah, so well, what is u going to be? U2 is going to be, that gets even worse, right? Well, it's not quite V2. What we have to do is we have to remove from V2 the portion of V2 that was parallel to Q1. Does that seem reasonable? You've decomposed vectors before, right? So let me draw. I'm not trying to necessarily do a representative drawing of that, but if this is V1 and this is V2, I can think of V2 as being